So with this sad situation, and it's continued now for years, we were working at Oak Ridge National Laboratory to develop an instrument or instruments that people could make for themselves and that was reliable, and also that it didn't depend on batteries or special facilities for repair that ordinary people, even if they're quite expert at some things, they just haven't got that capability. Well, to make a longish story short, this little instrument here meets many of those criteria. I'm not saying it's as good as a really well-designed and made radiation monitoring instrument, but it is dependable and it is accurate, and people by the thousands have made them for themselves. The trouble is, we'll look at it a bit later, but it looks like a toy, a little piece of junk, and Americans are used to, we're all used to using instruments. In most cases, we don't know how they work. We certainly can't repair them, but you can, you push a button or you twist a dial and out comes the answer. And so this does not have, you might say, appeal. It's not the kind of thing that most Americans would want to bet their lives on. Well, I've been encouraged that some people have concluded otherwise, and the technical Oak Ridge National Laboratory report on this instrument went out a few hundred copies, but obviously one of them fell into the hands of some of our British friends, and I was really surprised to receive a copy of the Journal of the Institute of Civil Defense. This is the premier society for disaster studies in Great Britain, England, Scotland, Wales. And it is the complete patterns and instructions taken from the first Oak Ridge National Laboratory report to enable a person to make this simple instrument. Here, for example, is the wraparound pattern that goes around a standard 8-ounce, or for that matter, a variety of other cans. I didn't know it before I got into this work on instruments, but our can-making machines, they make the big ones, the little ones, you see the same diameter. And oddly enough, pop cans and beer cans are also the same diameter. So, as I'll explain in a few minutes, the problem in this country of getting a can of the right size is quite simple, and you can use cut down the can to the specified height if you don't have an 8-ounce can. Well, the first detailed instructions that are similar to what are available today, they came out in the first issue printing of Nuclear War Survival Skills. This was and is an Oak Ridge National Laboratory report, not copyrighted. Anybody can reproduce it that wants to. But that has its good points, and it also has its bad points. The first reproductions were made by a nonprofit defense-related organization, the American Security Council. And these were sold quite widely, some in foreign countries. Even before this came out, the National Technical Information Service of the U.S. Department of Commerce got out copies, and they sell right now for $22.75, and the price is still going up. They're exactly the same as the Oak Ridge National Laboratory report. Then other people got into the act, and this one, you see, 1995, at a time when the government ones were selling for less than $10. So then there's cheaper ways of, I think Franklin remarked on that, I don't remember the exact quote, you can make a cheaper version if you photo-reduce it. Here's one that they just shrank. It has the same patterns, but they're absolutely unusable. The text refers to an 8-ounce can of this standard circumference, and to put this is an utter impossibility. But there's no penalties, and it saved the producers money, and the people that buy it, they don't know the difference. Fortunately, later editions, Oak Ridge National Laboratory sent the organization that got out these negatives with shrunken margins, you might say, so that they were the right size. But people, from reading it, you can't tell which is which. Here's another Oak Ridge National Laboratory one, and there have been quite a few other reproductions. Over the years, both based on what's been done in this country and other countries, we have improved the instructions somewhat. And so there's even better instructions in here. And there also, you have the instructions with index numbers. You notice on the back of all these sheets, they're index numbers. And the reason for that is, here's that wraparound pattern, that in a crisis, that is a prolonged crisis, you could expect that some people would want to get these reproduced quickly in newspapers. And if you have a paste up, a cutout, that this has been worked out so that it makes a 12-page tabloid, a standard tabloid from the Atlantic to the Pacific. Those are standard all over the United States. And this way, all of these pages can be quickly cut out, pasted up where they photograph them in a modern newspaper office. And we've run tests in 2 different newspapers from the time they got the instructions to the time the presses were rolling with this tabloid, 12-page tabloid, around a half hour, 3/4 of an hour. Well, let's get back and look at how this simple device works. Well, first I'll talk about its general principles. It's basically an electroscope. Electroscopes were used for many years by the scientists who investigated and made the basic discoveries of the nature of the atom and the radiations that some isotopes set off. So most electroscopes are made, I'll take the top of this off. Well, I'll charge it first. Most electroscopes have one leaf, and the leaf is very light. This electroscope has 2 leaves for reasons that are a little complicated, but it works. And they're decidedly heavy by the standards of an electroscope. Each is made of 10 thicknesses, or rather 8 thicknesses in this model, of just standard aluminum foil. And I suppose, I don't know why all the different brands of aluminum foil are very, very close to the same weight. So you have all over the country aluminum foil. You also have cans, you also have thread or dental floss, you also have bell wire, other wire, and everything that this instrument needs is in, I'd say, every village and usually in every neighborhood in the United States. It's, besides being an electroscope, it's what's called an ionization chamber. That is, there's a chamber, this is just the volume of this can, and it's covered with clear plastic, as you see. And I'll show you how it is charged, which requires no batteries. And over the years, many instruments that require batteries, well, batteries give out. If they're not changed in a private one, of course, they start falling apart and can actually ruin the instrument. This is charged by quite a number plastics are good charging material, and you generate several thousand volts by merely rubbing dry paper and one of these plastics. This ruler works quite well, gives the opposite charge to this piece of plexiglass, but both are equally good. And so you have several thousand volts on this plastic. And when you bring it over, now a spark jumped and separated the two leaves of the electroscope. You can see the stop threads on the side that keep the leaves, if it's tilted this way, from bumping and then on this way. And the very high voltage, it's so high that if you, even with this insulated wire, if you touch the leaves, see what happened? They go together. It bled off through the light insulation and, of course, to my body and to ground in that way. It can also be charged by unrolling tape, such as PVC tape or Scotch tape and some other kinds of tape, in which you have a direct conversion of mechanical energy to a high potential, about 20,000 volts. And there you see it jumped. You can't see it, but I'll tip it up. I raise the charging wire and hold it in the down position, because otherwise the tip of the wire is too close to the leaves and you can get a discharge, or at least a leak, a slow leak. You can carry it in a car, you can carry it in your hand, you can even put it up on a pole and stick it up out of a shelter to find out what the radiation outside is. Well, getting to how it works, you have, as I've said, a radiation measuring device that depends on the principles of an electroscope, a two-leaf electroscope, and also on the ionization chamber. And some people have made these thinking that any size can will work. Well, all these dimensions are interrelated, and you'd better stick to the instructions or you will get an instrument that is not accurate. Inside here, you can't see it very well because it's blue, but a drying agent, this one has silica gel in it. You have to go to a chemical supply house, or some camera shops have some left over. But that isn't practical if in a prolonged crisis people were making these. You'd better use homemade anhydrite. Now, all over the United States, there's wallboard gypsum. Here's a piece that's taken out of a house, and you see it even has paint on one side here. This, if broken up in pieces and just put it in the oven. Well, I can't, here, I can break up some right here. Well, I'll just break a few pieces, and that material, if heated, it drives off the water of hydration. This is hydrated calcium sulfate, and you have what's called anhydrite, which is calcium sulfate. And that, with some coloring on it, is a laboratory-grade drying agent. So you notice the one you just saw has white stripes on the end of its leaves. This instrument is in this jar with some drying agent, as you see in the bottom of it, and that keeps it completely dry all around. Unfortunately, all of these clear plastics are permeable to water vapor, which means that in days to a week or so, you have to replace the drying agent in them.